Great pleasure today to welcome Roy Want, who's going to be talking about next generation Wi-Fi positioning. Roy Want received his doctorate from Cambridge University in England in 1988. He's now research scientist at Google. Previously, he was senior principal engineer at Intel from 2001 to 2011, where I originally knew him from. Before that, he was a principal scientist at Xerox PARC. He's a fellow of the ACM and the IEEE, and his research interests involve indoor positioning, mobile and ubiquitous computing, context-aware applications, electronic identification. He received the ACM SIG Mobile Outstanding Contributions Award in 2019. It's a great pleasure to have Roy here to tell us about the latest in Wi-Fi positioning, and I'll turn it over to you. Thank you so much for being here, Roy.
Josh, thank you very much for inviting me. It's a great pleasure to be here. So next generation Wi-Fi positioning, why have I come to talk to you about it now? The answer is that after about 6 years of work, we've published the standard 11az as an amendment to the baseline standards. So that was in March 2023, and it will be rolled into the new baseline in 2024. And it basically deals with a lot of the issues which prior Wi-Fi standards associated with the location didn't solve. And I'm going to talk to you about that today. So first of all, a little bit of background on Wi-Fi positioning, some of the limitations of the previous protocols, and then we'll get into the details of 11az, how it deals with scalability, the issue of dynamic measurement rates and how to make that efficient, the accuracy that you would expect and how it improves upon previous accuracies, security, the performance from some interop testing that we've achieved already, and a quick summary. And then we'll go to questions. So I won't dwell on too much of the pro forma, but obviously indoor location has many applications, particularly in retail, finding your way to a product in a store, store analytics, customer flow. In the enterprise world, which all of us work and live in, indoor navigation still applies as being useful, smart office services, asset tracking, possibly also document rights access, although we haven't seen a lot of that yet because it hasn't been generally available. There's also other areas. You may have seen Google has a Better Together program, which is all about how devices have more value when they're together. And that means detecting that something is within the range or within a certain distance. So contextual information, such as, I might to a smart speaker say, turn on the lights. I speak in a very imprecise way, so it doesn't know which light, but perhaps it's the one which is closest to me. Or you might want to transfer some information or a photograph because devices are proximate. And then finally, the other big area is security, which has been really driving some of the thinking about wireless proximity or location protocols in recent time. So that proximity being a second factor for security, allowing you to access a venue, unlock a screen, for instance, if two devices come together, and things like keyless car entry and an engine start due to not only a key, but also the proximity of the key being close by. And we'll get into all of those very shortly. So now a little background on the generations of Wi-Fi. And you can think about us having 3 generations to date with the 11az standard. The initial work was basically done with RSSI. It wasn't a standard. It was a signal of opportunity that companies or researchers took advantage of. And of course, Microsoft Research, Victor Ball and the famous radar paper was one of the first to do that and capitalize upon it. Later in 2017, we had FTM, which was a revision of the existing baseline at that time. And this can give 1 to 2 meters at 80 megahertz of bandwidth. But it hasn't been widely deployed at this time, although those numbers are increasing on a yearly basis. And I can talk to you about that a little bit later as well. The third generation is really the basis of this talk, which is 11az, where we expect to have 1 meter of accuracy. The bandwidth available increased to 160 megahertz. And most importantly, it scales to very large numbers of clients. It builds on all of the wireless protocols that we know improve in the bands that we're using, such as MIMO support. And of course, it adds on this secure and protected ranging, which we'll talk about. So, and just to give you a tidbit, it isn't finishing there. There's currently work on 11BK, which is the 4th generation, which adds 320 megahertz positioning. And if you are following the other capabilities, such as UWB and Bluetooth channel sounding, UWB has 500 megahertz of bandwidth. So 320, 500, it's getting very close there. And with some of the other capabilities of Wi-Fi, actually is pretty competitive in this space. The reason I put this slide in here is that you can't really just talk about one radio standard without having the context. And UWB and Bluetooth channel sounding are the main competitors. The secret power of UWB, of course, is the accuracy with 500 megahertz of bandwidth. The accuracy basically being proportional to the bandwidth. The key thing that I want you to take away from this slide on the chart on the left, without going into all the details, is that accuracy is only one of the dimensions. There are many other issues related to range, particularly if you're using it for navigation, services, which you may be running on the network as well. So for Wi-Fi, it's obviously data services, and to have one radio with one solution is a huge benefit. And also coexistence with other radios, the ability to detect and back off when the channel is busy. And that sort of takes me to the right-hand chart. Just a quick look at the spectrum. You can see that Wi-Fi has officially mandated areas of the spectrum, which are sitting there at 5 and 6 gigahertz and 2.4 gigahertz. Other technologies are kind of in that spectrum, but they have to coexist with Wi-Fi. And so, for instance, one of the channels that UWB was going to use is right in the 6 gigahertz band, where Wi-Fi 6 gigahertz has just been enabled by the FCC. So, so there's a lot of value in being part of a standard which is well accepted internationally across the globe, and is going to be there to stay rather than having to coexist with others. So, so that's sort of the background. And one of the reasons that I think Wi-Fi has a secret power also is that it's already ubiquitous. It's already there. Somebody has bolted access points to the ceiling and run power cables or power over Ethernet. And as we get these new capabilities like AZ, we are simply going to upgrade those access points. The cost is relatively low compared to any other technology, which would require a new deployment. So that's kind of the background and why I'm a firm believer that AZ and its derivatives is the way to go. I want to give a quick recap on 11MC, particularly if this is not something that you're that familiar with joining the talk. On the right-hand side, you can see a graphic of an application that is freely available on Play Store called the Wi-Fi RTT locator. And you can see in our tests, some of our test environments, this is the kind of accuracy you expect. We're actually following the aisles between the cubes and the offices, conference rooms there. And you can see it's tracking pretty nicely. And the kind of errors that we get are 1 meter at the 50th percentile and 2 meters at the 90th percentile, to give you a perspective. So how does it work? Well, the basic principles of all of these Wi-Fi design protocols like MC and AZ is time of flight. Basically, if you know the time of flight of an RF packet, which travels at the speed of light, multiply the time of flight by the speed of light, and typically we measure the time for a round trip, so we have to divide by 2, and that gives you the distance. We'll talk about the accuracy later on in the talk. If you compare it to the signal of opportunity Wi-Fi signal strength, you can see on the right-hand side the color boundaries between equal signal strengths, and those two phones would actually measure on the right-hand side the same signal strength, but of course one is twice as far away from the access point as the other one. And so that's the nature of constructive and destructive interference which occurs in these kinds of environments. So time is by far the best way to go. And on the left-hand side of this chart, you can see the basic principle of operation, which is the phone initially detects an access point which has 11MC capability. This is because a bit is set in the beacon. It makes an FTM request to the access point. The access point then at some point will send this new kind of packet, which they introduced called the FTM packet, or fine timing measurement packet. You think of this as a ping. It responds with an ACK, which is received. The original FTM was transmitted at T1, received at T2 at the phone. The ACK was transmitted at T3 and received at T4 back at the access point. In order to calculate the distance, we need to have these 4 timestamps. And you can think about this as a sort of a quick summary, that T4 minus T1 give you the total round trip time. But T3 minus T2 gives you the turnaround time at the phone end. So if you subtract the 2, you end up with the round trip time. The only problem with this picture so far is that one side has 2 timestamps and the other side has the other 2 timestamps. So another message needs to be sent which conveys one to the other. And the choice was to give the phone the timestamps. And so the access point sends T1 and T4 to the phone. In fact, on the next FTM ping ACK part of the protocol. So in fact, in reality, you would perform a burst. An Android, for instance, I can tell you the default is set to 8. So you get 7 measurements as a result of a burst of 8 of these. So that's the basic principle. So keep that in mind as we go into more complex scenarios. I will also just point out one thing. In terms of packets and figuring out timestamps, the transmission T1 is an easy timestamp to figure out because it's the time which you rolled the buffer out onto a clear channel. T2 is the receive time at the phone, and T4 is the receive time at the access point. These are hard because you receive this packet which is bouncing off of the walls, all sorts of phase shifts and amplitude changes have occurred. It's very difficult to tell exactly where that packet starts. And this is part of the magic of signal processing in order to recover those timestamps. And again, we'll talk about it more as I get into the security side of AZ and how you can be sure those timestamps are what we think they are and what the bounds are. Just for completeness, on the right-hand side, I just wanted to show that the process of actually forming a position or calculating a position is where you have ranges is multilateration using multiple distances to access points at known positions, and this to determine a position is really a case of minimizing the errors between the ranges that you have measured and the ranges to the point which you assume the phone to be at. So if you minimize those errors, you get the optimal choice of position. But there's lots of other things you can do with filtering, such as particle filters, multiple range Kalman filters. But that isn't the scope of this talk. We're trying to talk about how we get the ranges that we're going to use. And I wanted to introduce this graphic to show you how I'm going to talk about 11az. So the time chart that you saw a moment ago with the burst, the implication of the burst is actually shown here. You can see the negotiation with the FTMR, the FTM request and the ACK, and then the FTM and the ACK, and the FTM and the ACK all the way down to the end of the burst. So this is the terminology I'll use for 11az. One of the things that you can see here is that one of the problems with MC is that there is a gap between the original request and the next FTM, and then the next FTM. So in other words, the ACK and the FTM occur one after the other in what's called the smallest interframe separation. But the gaps between the FTMs it requires the station to reacquire the channel. So if you're unlucky, another station can get in there, and that will make the whole process of obtaining your burst estimate very lengthy and possibly you'll time out the whole process and have to redo it again. So that's one of the problems of scalability. There's also no security in these packets. So all these timestamps are visible. And if you're a smart attacker, you can figure out ways of overlaying the information on those packets. And so you could corrupt timestamps. There's very limited diversity in the original definitions. So there's, it could be solved by going to full MIMO. One of the things to think about is that the reason for doing the burst, perhaps I didn't mention it, is that you want to average the range estimates that you get. So you're having to get a large number of these to average them to get a result. And if you can do that in parallel, for instance, by using MIMO with multiple range estimates between combinations of antennas in a MIMO multi-antenna system, then you can do this in a single shot rather than having all these additional exchanges. So that's what we're attempting to fix in 11az. This is why next generation positioning begun, and this was a task group that started in 2017, has been working towards this last year. Okay, I'll just pause there in case there's a quick clarification before getting into the AZ side of things. I don't see any.
FTM stands for fine time measurement, or?
Say again.
What does FTM stand for?
Fine timing measurement, yes. That's exactly that. So in other words, it was a kind of packet which the firmware and the hardware would attempt to create a precise timestamp for when it arrived.
So do these standards use multiple antennas for angle of arrival measurements, or is it mostly only time of flight?
They can, although typically you haven't got many antennas, so the accuracy of angle of arrival would be fairly crude. But folk are thinking about it, and in fact there's a 60 gigahertz version of this as well. I won't talk about it today, but of course the opportunity is far greater to have real angle of arrival on 60 gigahertz. Okay, so next I'd like to get into the phases of the protocol. So I'm dividing this basically into 4 pieces. Initially, there was security establishment, which again, I won't go into it. It's really part of existing protocols such as 802.11az or OWE. Think of this part of the protocol is that we can get a pairwise keys between devices which are secure and unique. So now we can then apply those keys to the remaining part of the protocol. The next phase is negotiation to decide what kind of ranging process we can have. And then we'll have the measurement exchange, which is also known as sounding, and we'll do this n times. In the negotiation, unlike MC, which we had to redo it for every time we wanted to start a new burst, the plan is that we only do this once. And then at some point, we get to a stage where we will terminate that particular ranging session, which could be done because you literally time out, there are no more packets within a certain time, or it could be done explicitly. So let's get into the negotiations. So what kinds of things would we want to negotiate? Well, there's the basic RF5 parameters, such as the bandwidth. There may be security parameters, so whether we want security at all and what level of security we want. There is also what our scheduling plan is for exchanging measurements. Whether, and this is quite important from the point of view of acceptance, what is the privacy policy? Is it only the client stay that receives the location measurements in the end, as I described in MC, or is it both ends? So the policy can actually be negotiated with AZ. So either just the client receives it, which is kind of the state of the art, if you like, now with 11MC and smartphones, where you want privacy for the clients, and obviously Android, Google requires this for all clients, but it doesn't necessarily mean that all stays are in this category. So there's also a policy which you could have where both the client and the network receives these measurements. So an example of a device which would fit in that category would be something like a barcode scanner, by one of the companies like Zebra or so, where it's obviously important for the scanner to know where it is, but likewise, the whole system, which is performing some sort of asset tracking or inventory management, can also know where those things are being scanned. So you know where devices end up once they're being scanned. So there are other parts of the market that we are addressing with this protocol to make it practical and adopted by all parties who may then build the market and make it more available for the rest of us as it becomes ubiquitous on any product that you can imagine. The next phase of negotiation is the next phase after negotiation is the measurement. So this is sounding, and there are two aspects to this. One is the non-trigger based sounding, and then there's trigger based sounding. So I'm going to get into these in some detail, and this addresses the issue of scalability. So how does this work? Well, the first thing is that recognizing this issue of the MC protocol having multiple components of which another station could potentially break into the middle of because they got the channel first. This is now done with a single TX op. So in other words, once you start this sequence, which you can see at the bottom of the chart here, then the sequence goes to the end. It maintains the channel. And the other thing is that the packets which are actually doing the sounding are these NDP packets, which you can see here, UL NDP, uplink NDP, and downlink NDPs. These are PPDUs, so they're PHY packets with a null MAC payload, and you're just using the transmission of those packets and the OFDM preamble in order to determine the time of arrival for those packets. And furthermore, they're also it's also been designed that they're spatial, so that this whole process starts with an NDPA, which is from the I stay up to the R stay. So we've already discovered the R stay and negotiated and so on. So now we're doing this sounding. So the NDPA tells the R stay which antennas are transmitting, and so we get a spatial encoding of these packets, and we know the arrangement because of that NDPA. So the access point can then receive that, and then it responds on each of its antennas. So again, it's a spatial response, and now we have the downlink NDPs, and that's received, and we can calculate the timestamp we're receiving. And then before we talked about sharing the timestamps, so there's a new packet, which is the LMR, Location Measurement Report, which then will share the timestamps which the RSTAY, the access point, RSTAY being responder stay, I haven't said it before, the access point responds and tells the iStay what those timestamps were, so then it has all 4 timestamps and can calculate the time of flight and the distance. So that's non-trigger based. As you can see, it's a single TX op capability. For true scalability, 11az takes advantage of Wi-Fi 6. And so this gets a little more complicated, but it's kind of interesting the way things are going. So this is trigger frame based scalability. And the way that this is done is, if you like, the Wi-Fi, was traditionally a CSMA protocol, and so everything was basically randomized, and you had random access to the channel and so on. Now the Wi-Fi world is moving a little bit closer to the scheduled world of cellular systems, where there are sort of time slots where things can happen, but the time slots are still randomized, in the sense that what they've done is they've added this thing called a trigger frame. So what happens is the RSTAY sends a trigger location polling frame. So this is a type trigger frame. And what happens is all the stays which negotiated with the access point to be able to respond in a certain time frame are responding here using another aspect of Wi-Fi 6, which is that they can send a clear to send to themselves, a CTS to themselves in a particular narrow range of frequencies. which are called resource units. And so these all together, the list of these is defined in the trigger frame. And so they hear the trigger frame, and then in synchronization, they all transmit in exactly the same time slot, but they're at different frequencies. And so they're all here and they don't collide with each other. All right, so now the RStay knows which of those iStays are ready to perform sounding with it. So they're all synchronized. When it decides which subset of these, because it doesn't have to choose them all, it may know what times are critical because of the negotiation that's had earlier. It will then send another trigger frame, but this is of type location sounding. And the consequence of sending that, which also has a list of the iStays that it chose, will be a set of NDPs which are sent from the stays up to the RStay. And again, this is a spatial encoding so that each of these are overlapping each other, but the RStay can pull them apart. And I'll talk a little bit about that in a second. Then the response coming down, again, the RStay may have multiple antennas, so it will need to send a spatial response. And exactly which antennas it's going to use to send that response will be encoded in this packet called an NDPA, which is a null data packet announcement. So that the list is in here. This is what's sent. Everybody receives this on a broadcast. This is what's sent. And because you know what's in here, you know what parts of the packet to pick out in order to calculate the downlink. So now you have the time for these. And then finally, there is a location measurement report, which contains the timestamps which you don't have at the iStay. The one thing that's different in this protocol is that in response to the LMR downlink, you can also send an LMR uplink. So if you negotiated that the access point could also get this information, and one more packet would be sent at the end here to provide that information. Okay, so the next important thing that 11az has done is that it's created this ability to have a single negotiation and then a dynamic measurement rate. And so in the case of NTB, it's just between one stay and the access point. In the case of TB, it was between multiple stays and the access point. So in this case, with a single one, in the negotiation, you also negotiated a time window, which is a minimum ranging period and a maximum ranging period. The minimum ranging period is so that the iStay doesn't swamp the access point with too many requests. So, and if they'd set too low a value, the access point, which may well be busy, right? It may have a video stream on with another station at that time. It will choose what it considers to be the minimum. So it's a negotiation. And then there's a maximum ranging period, and typically this might be used as a timeout. So if you exceed that, then we'll shut down the thing. But everything in between the minimum and maximum ranging period for the session is game. And the iStay, for instance, which is typically a mobile device, may well decide that it wants to have less measurements when it's still and more measurements when it's mobile, which makes a lot of sense because you want to better catch, when you've turned the corner and so on, when you're navigating through a building. So there's lots of very good reasons to do that. And also you can limit power as well, because if you're still, you clearly can avoid making transactions that you don't need to. And also you respect the bandwidth of the system so that other people can use, or other stations can use the spectrum, and you're not hogging it, setting it at a fast rate. So generally it's a good thing. With the trigger-based one, it's more complicated because you need to fit in with the time map for lots of different stations, and they all may have their own requirements for when they can transmit. So the way the negotiation is done is that part of the negotiation will ask for a map of all the times when you cannot possibly transmit. So in other words, it's a negative scheme, so that you're looking for the times which are impossible to transmit. So now you give a lot of possibilities that the R state, the access point, can combine different stations requirements and still end up with a viable scheduling schedule. So typically what will happen is there will be a number of ranging measurement opportunities. It will know which of the stations are likely to be able to respond. It can use the polling frame to validate that and to choose which one it actually does sounding to at that time and figure out what the timestamps are. So that's the flexibility that we bring. And next thing to think about is other forms of scalability, which different protocols other than Wi-Fi have used in the past, and Wi-Fi has adopted. So the intriguing thing about this kind of system is that it is possible to make a totally passive location system where the mobile devices do not transmit anything. They just listen. And if you think about it, this is similar to GPS. That's how GPS receivers work. They just listen to signals from the satellites that are orbiting and encode their position as they send their signals. It's also very similar to something called LoRaN. In fact, more precisely similar to something called LoRaN, which is used for shipping before GPS. And I think I'm right in saying that ships still have to maintain some sort of LoRaN capability in case GPS goes out for some reason. And essentially what these systems do is they use differential time of arrival. So if we look at the center graphic, what you see are two stations which are beaconing in total synchrony. So they'll create two radio beacons which the master clocks have been synchronized through some technique. And obviously it could be through exchanging messages between them, or it could be some other master clock which is being used. Now, if you receive those two beacons, these hyperbolas show you the time of constant or lines of constant time difference. So basically, by measuring the time between those two beacons, you'll know that you're on one of these hyperbolas. And you can do exactly the same thing with Wi-Fi and wireless. And you can see on the right, I've got a little MATLAB simulation which shows how you can use intersections between different pairs of access points if they were beaconing at exactly the same time, and how those hyperbolas will intersect in one unique point, and that's where your phone device would be. So now the question is, how can we take advantage of this in practice? How can we use Wi-Fi to make this happen? And there is a mode which has been put into 11az, which is called passive ranging. And it typically works by one of the devices would be chosen as a controller, which would range to other access points which are within ranging distance. So imagine in the grid through your building, there'll be groups of these which are situated like this. And all the phone has to do is it has to listen to these exchanges, these 11az or FT. It can even be done with FTM, although it's not part of the standard with FTM, with 11MC FTM here. But of course, the problem is that these APs are not synchronized. So how could we use the protocol as I've described it to you already in order to make them appear to be synchronized? So here's an I stay and here's an R stay on the right-hand side. And you can see our phone is a P stay, standing for a passive stay. Here we have the T1 to T4 round trip time, which we talked about before. And then the turnaround time is T3 minus T2. So imagine T1, it transmits and it's received at T2, but also at the passive stay, it's received at T5. At some point later, it sends the ACK, and so we've got T3, which is also received by the passive stay at T6, but also the I stay at T4. Now, if we look at the time difference between T6 and T5, we potentially have a time difference arrival, but the problem is that these two packets were not transmitted at the same time. However, we can actually correct using the components of the protocol. We can correct for the fact that they're not at the same time. So if we look at the time T4 minus T1, which is the total round trip time, and we subtract one of these legs here, the bottom one, which, as it turns out, is the distance between the access points, which is fixed because they're bolted to the ceiling, and divide by the speed of light, then this turns into a time. So now we have the time between T1 and T3 in this set of brackets on the right-hand side down here. If we subtract that from the difference between T6 and T5, hey presto, we have the time difference arrival as if they'd been transmitted at exactly the same time, as if these two packets have been transmitted at exactly the same time. And that's the basic principle of time difference arrival using Wi-Fi. The requirement, of course, is that your infrastructure vendor has to support this passive mode. And the standard, of course, has only just been released. So we'll have to see how that develops in the market. But potentially really interesting from a privacy point of view, of course, it's fantastic because the infrastructure has no idea that those stays, which are mobile, even exist. So there's no interaction with them. So, so now let's just talk about accuracy fundamentals quickly. You know, what kind of accuracy can we get? The derivation of this is beyond this talk, but there is something called the Kramer-Rao lower bound, which is an estimator for the time of, or can be used as an estimator for the time of arrival. And it resolves to this equation here. You can see that the range error is proportional to 1 over the bandwidth, or is great, potentially greater than that, and it's proportional to 1 over the square root of the signal to noise ratio. So what you get out of this is that bigger bandwidths, smaller errors, which we already know. If we can reduce the SNR, we also improve the accuracy. And one of the things I talked about before was figuring out when the packets start. And typically this is done by looking at the prefix of the packet which is sent, which contains all of the sine waves used in the OFDM encoding, the orthogonal frequency division multiplexing. And in so classic packets, there's one of these. But in AZ, we have the ability to have repetitions of these LTFs, the long training fields as they're called. And if you simply add the reception of these together, the noise is not correlated, but the LTFs are. So we actually boost SNR in these spaces. So that's another way which we can improve accuracy. However, that isn't the main cause of error in the system. Unfortunately, the main cause of error is because of multipath. And if you calculate the Kramer-Rao lower bound with a noise floor of minus 90 dBm, so typical, and say you're receiving your signal at, say, minus 50 dBm, then you would expect an accuracy of about 10 centimeters, but we get nowhere close to that at 80 megahertz. We get maybe a meter of accuracy. So the problem, of course, is that all these sine waves are bouncing off of the floor and the ceiling, and when they all combine at the receiver, we have a phase shift and we have an amplitude change. And unless we can compensate for that, we have further uncertainty in where that waveform starts. Now, OFDM, of course, uses hundreds of sine waves in its encoding, and so the training field actually has hundreds of sine waves in that training field. And so we get a processing advantage by looking at the time of arrival of the set of sine waves. In the case of AZ, we're using full MIMO. And so what we're basically doing is we can assume there was a path from one antenna to all the antennas on the other stay. And likewise in the other direction. So here, if the AP had 4 antennas and the client stay had 2, we've got a 4x2 system. So we have 8 paths. And so if one path had a particularly poor characteristic of multipath, that when many of the tones were almost canceled out and barely visible at the receiver because of destructive interference, then we would have other tones which were successful. And that's the basic principle behind the success of improved ranging with multipath. And you may wonder exactly how this is done. I talked about spatial encoding before. So when I mentioned the trigger frame being sent by the RSTay, And then we had 2 iStays responding. I'll just talk about it in one direction at this time. The actual packet which is sent has repeated LTFs. So you can see the repetition block here. But because it's a MIMO system, there are parts of the packet which are dedicated to the well, if you like, logically dedicated to the first antenna in this 2 antenna system, and then to the second antenna. And you could imagine, one way of sounding out the system is that just say in this iStay 1, just transmit a antenna. Sorry, we transmit from antenna 1, and then it's received by 1 and 2, and then we transmit from an antenna 2, and it's received by 1 and 2, and do this at separate time intervals, as we kind of have indicated here. But in reality, in fact, what you do is you pre-encode them, and you add combinations of either the same polarity of the signal or negative polarity of the signal. So here you've got a 1 and -2 and a 1 and 2. If we add these up at either antenna, we either get 2 1s and 0 on 2, or if we subtract them, then we get the signal from the second antenna, and the first antenna disappears. And that's preferential for this kind of system because it maintains the amplitude of the packet that you're receiving throughout. And if we were to change the amplitude of the packet, then we're going to mess with the AGC and cause other problems for just the hardware of reception. So that's how it's actually done in practice. But the important thing is that we can get all the different paths from one device to the other.
I think Shav had a question. Shav, is that a clarifying question?
Yeah. So I guess when people use time of flight for localization, they make different kinds of assumptions. One assumption they can make is that the line of sight path exists, or they can make a stronger assumption that the line of sight path is the strongest path. Do you know which of these assumptions people are making in this standard?
Well, I think the reality is there's always usually a line of sight. It just may be very attenuated. So what they are trying to do I would say, okay, to answer your question, that is not part of the standard per se. That's part of an implementation which all the big vendors will know what works well for them. And they've had to do a lot of signal processing in order to use these training fields in order to decode the data fields in the rest of the packet. So this is kind of reusing that technology in order to achieve this. I'll talk, if you don't mind, I'll just defer to a little bit later when I'm talking about security, which is coming right up, okay, where we'll talk about how we do time of arrival. Okay. Okay, so right on cue, security for MAC and PHY. So if you're thinking about protecting the location system, you have to say, well, what kind of adversary are we going to consider? So the first thing is that adversaries don't play by the rules, and they can basically do anything they want. So they can impersonate and falsify unencrypted message content. They can also transmit partial PHY layer headers with time advance, which I'll talk about in a minute. And they know all the characteristics of the signals which you're transmitting, so they can impersonate and overlay all those signals. Typically, if you have a packet which is transmitted, say the packet at the bottom here, an attacker could listen to part of the packet to synchronize itself, do some processing, and then decide to attack your packet by transmitting another series of pieces of that packet with different tones and different phase relationships in order to change the characteristics of this part. So let me go to an example here where there's an attack by some nefarious people here who are trying to steal this car, and all they're going to do is they're going to bridge the wireless key, which is somewhere maybe in a bowl near the door of this house, and this car over here. And all they're doing is they're bridging the signals, the radio signals. They don't have to understand them, decode them, or anything, but they're bridging the gap between those signals. And that gap could be 20 meters away, but of course the car was originally set up to only unlock maybe when you're within half a meter based on the signal strength of the encrypted packets. And so there you see they've got into the door. In fact, they have to do it a second time to do engine start. So I think a lot of people felt that encryption originally was enough to build a wireless key if you can keep the encryption keys secure. But then people felt, well, if we can then range, we can add that as an additional parameter that you have to be within, say, 0.5 meter and avoid the kind of attack that I've just showed you in that video. It turns out there are still other attacks. So in here you can see at the top we have a station or an AP, and we have an adversary, Eve. And Eve could actually fool the stay or AP into thinking one is closer than the other if it can change the time of arrival of T4. In other words, create a T fake rather than T4 in our ranging equation. And they would do this by creating spoofed time taps of the estimated impulse response of the channel. Now I'm going to explain exactly what that is in a minute, but the $1 million question is, how can you advance time? How is that even possible? And I remember when I first heard this, I thought that this was a ludicrous concept, because how can anything go faster than the speed of light? But in order to understand this, you have to understand how time is calculated, time of arrival is calculated. So I'm going to try and do this very, very briefly. The essence of OFDM is that we have a PHY packet with a MAC payload, and there's a training field. It goes through the channel, which is basically the environment which you're transmitting this in. And all the OFDM sine waves have their phases and their amplitudes distorted. But the clever thing about OFDM encoding is, of course, that the training field always has a known set of phases and phase relationships for all the terms that it uses. So the receiver over here receives the garbled set of sine waves. And if it were to represent these as complex exponentials and take the FFT as a result of the FFT of these waveforms, then we can find out exactly how much the phase and amplitude of each sine wave has changed by pairwise dividing each of them between the receive and the send signal. And this forms what is often referred to as the H matrix, or the channel state information matrix. And we can then do a Fourier transform on the payload and transform it exactly the same way as the training field has transformed, allowing us to regenerate the encoding, the phase encoding of the packets. As we're using typically QAM-based encoding, this allows us to actually correct the encoding before you try to decode what that QAM constellation is. So that's the basic principle, and that has been going on obviously in Wi-Fi for a while. Now, let's look at this in more detail. How do we actually turn this into a timestamp? Well, if we look at our packet in terms of we're receiving our packet over here, and we have the training field. Typically with OFDM, you wrap the end of the packet around the front, which is called a cyclic prefix. And we don't know exactly where the packet starts, because if you look at an OFDM packet on a scope, you'll see that it just basically looks like white noise with some reasonable amplitude. So we can get some correlation as to where it is, but typically we will start sampling at a certain point. And the idea of the CP is that we can always take a window which has an exact integer number of wavelengths within it. So we can actually do a perfect FFT without having to worry about the discontinuities at the end. What we really want to do is we want to find this time, say between the CP and the training field, which is an agreed timestamp, which all of the stations will use. So how does that work? Well, the H matrix, which we just calculated, is really the frequency response of the channel. So if we take the inverse Fourier transform of that frequency response, we get the impulse response back in the time domain. And if you plot that impulse response from a time sample, which was beyond the point of the where the training field begins, what we'll see is there will be an impulse, which will be that delta time from the point when we started sampling. And so if we take the time sample and add that delta t, that is our time of arrival. Now, to answer your question is, exactly how do you remove those multipath components? And the answer is that you threshold this value. These are examples. This was a MATLAB simulation with considerable, multipath, but you can see the multipath peaks down here. In reality, a lot of these peaks are really close up to the original peak. So the real problem is not so much the first point here, but you get a rolling top, which is really the sum of several of these. So you might tend to think it's a little bit further away than it really is. It is also possible. You do see errors in these systems as well. It could be for some reason that peak is a little bit low down here, and you're looking at this peak. But if one of those weird situations happens, typically like the next reading, half a second later, the situation has changed somewhat, and then you've got other sort of post-level filtering on your position estimate, which kind of deals with it. But it works, and there are other algorithms than this. This is sort of like a core algorithm that is used, but you can also use things like the music algorithm and various other techniques in order to determine the first path. Okay, just to end this, the reason why I told you all of this is that basically with the old MC, the training field data exactly, so you can just replay it ahead of where you are. If you do that calculation I just showed you, this will force the impulse response to be much earlier than you calculated. And with AZ, basically we've added a huge amount of entropy into the phases here by modulating them with a variation of the encryption key that we created in the very first part of establishing the security context. And now if you do your listen process to figure out what those phases are and then try and attack, you haven't got enough time really to deal with the entropy. I mean, maybe one day in 10 years when you've got much more processing power in your hand, or maybe in the cloud, you can get it fast enough. Perhaps you could, but at the moment, enough simulations have been done that people are pretty sure that you can't attack it this way. This is part of the standard, so I just quickly pointed out that you can see how this has worked, but this is the derivation of the key. The net result is that the two sides know what the scrambled phases and amplitudes are, but the attacker doesn't. So they can still do the calculate the CSI and the channel state information, and the attacker can't and has to process everything to figure it out. Okay, performance real quick. So the performance was measured for an early version of the system to be in Broadcom with a 2x2 and an XP a 4x4 last July in the Wi-Fi Alliance Santa Clara labs. And they've kindly allowed me to share this with you to show you that here we've got measured range against actual range, and then 30 seconds, I think it's 30 seconds, or a good number of seconds recordings. That's why you get the smears here showing you, they should be on the line, and they are on the line, but there's some variation as you go across. And if you look at the error CDF here, you can see the CDF for 50th percentile is 0.16 on this experiment. Admittedly, it's on a bench, line of sight. CDF 90 is 0.38 and CDF 95 0.42. So first experiment, I'm sure they want to improve it more, but that was pretty good. And MIMO is doing a good job of removing the multipath, because this is, although it's a lab bench, it's an office type environment, and there's multipath everywhere from the ceiling and the surrounding walls. So so nice first result. There's another interop coming up next week, as it turns out, and so we'll get some idea of the improvement in that time. So just to finish with my summary slide, one of the key things that make Wi-Fi successful is that it has a superior link budget to a lot of other wireless technologies which are in this space. It has available bandwidth, it's allocated. It has compatibility with previous generations, and it will be part of a long series of Wi-Fi implementations which are replacing previous Wi-Fi implementations. So you expect it to be around for a while. It's not a flash of the pan technology. With this new protocol, it's scalable, it's adaptive to traffic conditions, it's robust through MIMO, and with the new PHY security, it's well set up to be robust against the known attacks that we have at the moment. All right, and I think I'm still just a fraction under time, so thank you very much. We'll go to questions, and I'll just leave an acknowledgement of some of the main people that I've worked with during the development of the standard, particularly the task chairs, Jonathan Segev, Asaf Kasher, who are regulars, obviously at the standards meeting, and then all of the industry contributors from Ali Rossini and Christian Berger, Nehru, and so on. Okay, I'll go to questions.
Thank you very much, Roy. That was great. I have some questions, but I'm sure other people have questions as well. So if anybody wants to jump in with a question, they can. Otherwise, well, I'll start with, oh, Sean, were you about to ask?
Oh, I can start with the question while other people are ready. So Roy, I think one of the things which stood out to me was when you talked about the accuracies, it's clearly very related to the amount of bandwidth you're using. The
Yes.
higher the bandwidth you're using. So it's kind of approaching UWB systems in terms of not approaching, but it's kind of like trying to leverage the fact that like the higher bandwidth which UWB has gives better resolution. MIMO helps in terms of multipath. So I guess the question really is it fair to conclude that the real change which has happened here is that Wi-Fi had moved away from 20 megahertz now to support 300 megahertz, and as a result, it's opening up all these positioning capabilities?
Well, that's certainly part of it. So Wi-Fi has been on a progression to get higher and higher data rates, and so they're requiring greater bandwidths. They're requiring coexistence across a band. So if you have multiple cells, you want to better color the frequency spectrum and so on. So all those things are driving just the data alone. But then it turns out at these higher bandwidths that we can also create more and more accurate range estimations. So it's kind of a bonus, I think, for this industry that we've now got this capability, and it's advanced to a point. I think, and I've tried to make the case that I think that it will be a very effective positioning system as these products begin to appear in our mobile devices and access points.
So when will the first AZ products be available, or are they already available?
So it's a two-part question. The first part is that this is all built on Wi-Fi 6 physical layer waveforms. So in other words, I think you'll find if you do a Wi-Fi scan in your university, there'll be a lot of 11AX, which is the acronym for that task group, a lot of AX devices which are in your vicinity. I suspect that most of those with additional firmware can support 11AZ. So in other words, it will be a firmware upgrade in order to be able to run this. And then of course, Wi-Fi 7 also would be able to run it too.
Got it. Another thing I was wondering is I've heard recently that there's efforts underway to create secure GPS systems. At least there's a research satellite being put up by the DoD soon, or maybe it's already up, that's for this. I'm just wondering if you're familiar with that work and if the sort of security philosophy is the same. I assume the attacks are a little bit different. It sounds like the car relay is kind of one of the main motivating scenarios for this.
I believe. I think the scenarios are similar, but they don't use OFDM, right? They use a chipping spreading technique. So to be honest, I don't know the mechanism. Galileo in Europe, I think, already has security built into their system. So really, GPS being one of the first has kind of lagged behind, and I guess they didn't really consider it to be a problem initially, but now obviously it is a known problem.
So if I ask another question, so these things are great for ranging, and as you mentioned in your talk, like if you want to get the exact 2D location you need to do trilateration, but then you also need to know the exact location of the access points.
Right.
So from an application perspective, for someone who's not really that tech savvy, for them to exactly say what the exact location of the access points is, and it seems like a lot of overhead in terms of deploying the infrastructure to be able to do 2D localization. If you assume that you need to know the locations of the
Right.
access points. What are your thoughts on that, or what the industry is thinking about that?
Okay, well, industry with the protocol, I didn't go into it because it's sort of more on the positioning side. But as part of even the 11MC protocol, there's something called LCI, which can be added to the packets, which is location configuration information. And basically, this allows the access point to tell you what its lat long, altitude, height above the floor, and even street address if it wants. So there's a known encoding which can be sent. And obviously, the other part of this is, well, that encoding has to be set by somebody in the facility, right? So in your university or your business, it has to be there. So that is somewhat of a burden for the IT administrators to do, and I agree. But that, again, it's like one of these sort of value trade-offs. So if location is important to people, then you do it once, and it's largely solved. However, there's been an additional development which is very exciting, and we can thank Aruba, which is these days is HPE, because they have something called Open Locate, and Open Locate uses access points which they've deployed in their system, because they're the second largest access point vendor, and they will ping each other typically at like 3 o'clock in the morning to determine their relative topology. And then they typically say, supposing you had 30, 40 access points in an environment, they would have a couple of them which are by windows, which would then use GPS satellites in order to determine their position. And again, they can average those satellite readings over long periods of time, so they can remove a lot of the jitter and errors that occur, and the satellites will move around and change position to give you the diversity. So then once the network has been formed, that lat long information can be calculated for everyone and automatically populate the LCI information, which then gets transferred to the phones or the mobile devices. So it's an exciting time in this field because the vendors are stepping up, realizing the importance of this and the ability to give you the positioning information that you need with very little effort to actually calculate a true position on the floor plan.
That is kind of cool to use distributed localization approaches for that.
It's nice that they've done it, and it's also partly self-serving, because when I talk to them, although we sort of think about access points being fixed in the ceiling, apparently, if you're a vendor of access points, the classic thing is that your vendor site remodels in some way, and the contractors just move things, right? And sometimes they move them in places that they can no longer even find where these access points are. So this system also allows them to keep track of where they are and make sure that the coverage is still good, and and understand where things have got to be moved to, or additional devices deployed in order to get the coverage they need.
Well, I guess I have one more follow-on question to that, which is, do you have any thoughts about how these maps can be made? I mean, obviously, Google has a big business making maps of the outdoors. Is there anything you can say about ways to create maps indoors? Is anyone working on that already?
Yes. Yeah. So Google has used crowdsourcing for a while in order to try and figure out where access points are, even for RSSI. So basically, it relies on the large population of Android devices, and if you tick the box which says you are prepared to help improve Android location, then occasionally a Wi-Fi scan will be done in an anonymous way, and the information aggregated to create a heat map of where access points are relative to known markers, like you may be near a window at one point and you get a GPS measurement. So then we gradually figure this out. And there's enough devices in the world, and even doing it infrequently over a period of time, you actually build a pretty good map of where things are.
I see Vaishnavi has her hand raised.
Yep. Awesome talk. Thank you so much for walking us through it. I was just going to ask if this feature will get integrated as a part of like RTT locator or any such a tool soon, because like location mapping would be really useful as opposed to adding that in.
So you mean the LCI part, or? Yeah. Yes, so actually it's already there. So if you pick up the very latest Wi-Fi RT locator, and your access points support the capability, if you put in the configuration file, if you put 0.0 for the lat longs, it will use the lat long in the access point instead.
We'll check that out. Thank you.
Yeah, so we create a new version probably couple of times a year. So it's good to track what's going on and you find these new features appearing.
Thanks.
Let's wrap it up here. Thank you so much, Roy. That was a great talk. Really excited to hear about this new capability. And thank you so much.
And thank you. It's great that I can come and talk about it and hopefully get others excited and start using it.
Thank you.
Thank you. Goodbye.